Okay, all right. All right, hello everybody. So let me recall what I proved yesterday for last. So we were considering the Sobolev quotient in the Euclidean space. So let me move this theorem. Okay, so we consider in Rn with the Euclidean metric. So we are in dimension n greater or equal to 3. We consider the Euclidean Sobolev quotient, which was simply some dimensional constant Cn, the integral of the gradient of u squared, divided by the L2 star norm squared of u. So here Cn is a dimensional constant for n minus 1 over n minus 2. And 2 star, I recall, is 2n, the critical Sobolev exponent. It's 2n over n minus 2. Okay, and yesterday I gave an idea about the proof of this theorem by Oban and Talenti. So in Rn, there are extremals of this Sobolev quotient, and a family of extremals are this function u and its dilations in lambda. Okay, so I defined u lambda of x as lambda to the n minus 2 over 2 u of lambda x. Here lambda is a positive constant. And in this way, we get a family of minimizers. So u is like this, and u lambda, when lambda large, would be like this. So this is u lambda, and this is u. And the point is that when lambda goes to infinity, u lambda converges, is still a family of minimizers, but it converges weakly to 0 when lambda goes to plus infinity. Okay, so another consequence or a consequence of this theorem is that you can understand the Yamabe quotient on the round sphere. So I recall that for a metric G, we defined QG of U on, say, on a compact manifold. We define QG of U as the integral of Cn gradient of U squared plus the scalar curvature U squared dV divided by the L2 star norm squared of U. And we define the Yamabe constant to be the infimum of QG of U for U in W12. Okay, and what we proved is that this is actually a conformal invariant. So a conformal invariant means that when you change the metric conformally, then y and g doesn't change. And there is a fact. So we understand this Yamabe constant on Rn, essentially, by the previous theorem. But the fact is that Rn, with the Euclidean metric, is conformal to the sphere minus the north pole, which I denote by Pn, with the round metric, GSN. Okay, so this can be proved using the stereographic projection. So which is a map that sends, so this is Sn sitting in R n plus 1. So this would be Rn. This is the North Pole. And this is a map that sends a point x of the sphere into pi, you can call it pi n of x. Okay, so pi n is a map that sends Sn minus the North Pole into Rn. And this is a conformal map. So it means that it preserves angles. Okay, so just to draw a picture, you have the sphere and two curves in the sphere that intersect with some angle alpha. You project using the stereographic projection pi n to Rn. You find the image curves, and the angle alpha is preserved. So a consequence of this fact is that actually the two manifolds, so Rn with the Euclidean metric and the sphere with the North Pole removed, but it could be any other point, with a round metric, so they are conformal. So a consequence of the previous theorem is that, so you have this proposition. So this is a consequence of the previous theorem. Is that the Yamabe constant of Sn with the round metric is given by n minus 1, the volume with respect to the round metric of Sn to the power 1 minus 2 over 2 star. So to see this fact, in fact, you can use the stereographic projection to bring those solutions in Rn, so which were given by this formula, to the sphere. Okay, and so let me copy the Yamabe quotient. So I just report it to the next page. Okay. And the point is that, so to see this, on Sn, the constant function u identical equal to 1 minimizes q GSN. Okay, so u identical equal to 1 realizes the Yamabe constant of Sn with the round metric. Okay, so therefore you just plug into this formula the function u identical equal to 1. So for u identical equal to 1, the gradient, of course, is 0 because the function is a constant. the scalar curvature of the round sphere. Let me write it here. So the scalar curvature of the round sphere is equal to n minus 1. Okay, and therefore, in this way, you just realize the optimal constant on the sphere. So if you insert a u identity equal to 1 here, so this term is gone. The scalar curvature is n minus 1. And then here you find the volume of the sphere if you take a u identical equal to 1 and integrate. Okay, and in the denominator, you find the volume of the sphere to the 2 divided by 2 star. Okay, so therefore, you have an explicit value for the Yamabe constant of the round sphere. Okay, so this is useful because let me recall, so the Yamabe problem was the following. Lg of u equal to r bar u to the power n plus 2 over n minus 2. So Lg was the conformal Laplacian minus Cn Laplacian of u on the manifold plus Rg. And we saw that the sign of the constant r bar must coincide, so this is what we proved yesterday, with the sign of lambda 1, so the first eigenvalue of Lg. So yesterday we solved y for lambda 1 of Lg less or equal to 0. And today we're going to treat the case, today we consider the case lambda 1 Lg positive. Okay, and we saw that the solutions of the Yamabe problem can be found as critical points of QG. Okay, so a natural question is, so does QG admit a minimum? Okay, so this is tricky because we have an embedding it's a Sobolev embedding. So the embedding W12 of M into L2 star of M. So this is the maximal value P for which the Sobolev space W12 embeds in LP. But this embedding is not is continuous, but not compact. Okay, so it means that it could be So let me copy this. Nope. Okay, so it could be that you have a sequence of functions uk. So it could be that uk weakly converges to some u in W12 without having uk converges strongly to u in L2 star. Okay, so the problem could be the following. So if uk is a minimizing sequence for QG, then it might be that UK converges weakly to 0 in W12. Okay, so an example, you can imagine UK so think of UK sort of similar to a family of functions of the type u lambda k. So u lambda k are those optimal profiles in Rn, but with a dilation constant that make them very concentrated at a single point. So something like this. So you might have your manifold, which I draw here. So this is your manifold M. And you might have a minimizing sequence which behaves in this way. So this is possible because in such a case, you would have, so suppose you have a concentration happening at the point P. So you might have seen something similar in Yannick's lectures. Okay, if you have something like this, then you have that the gradient of UK squared behaves like a Dirac delta at the point P. And the functions UK to the 2 star behaves like a constant, say C bar times the Dirac delta at the point P, and the scalar curvature times Rg times UK squared just goes to 0 in L1. Okay, so this could be an enemy. So due to the non-compactness of the Sobolev embedding, you might have this kind of behavior. So anyway, there is a proposition due to Ban. Okay, so the question is how to avoid such a behavior. So the point is that if you have this kind of behavior, which is called the bubbling, usually, because typically the blow-up profiles will have, so you can prove that the blow-up profiles have asymptotically this form. So the form of an extremal of the Sobolev constant in Rn. And this is exactly the conformal factor given by the stereographic projection. So geometrically, if you take the Euclidean metric and multiply it by this conformal factor, then it becomes like a spherical metric, so like a bubble. So that's why this behavior is called bubbling. Okay, and the observation is that this behavior comes with a quantization. Okay, say observation is that if bubbling occurs, the energy is quantized. So you can prove that there must be at least some value that depends on the dimension in which the energy has to accumulate. Okay, so Oban derived a criterion to avoid this kind of behavior. So there's this proposition 2. Sorry, the previous one, I call it proposition 1. Okay, so the value of the Yamabe constant of Sn. Proposition 2 is the following. It's still due to Oban. Okay, so this is due to Oban. Same paper as before. So he proved that for every compact manifold Mg, one has that the Yamabe constant of the manifold is less or equal than the Yamabe constant of the sphere. And if you have a strict inequality, then Ymg, so which is the inf of Qg on W12, is attained. Okay, so I'll leave a proof written in the notes. I don't think I have time to go through the proof, but the idea is the following. So I said that so what is the enemy when you consider a minimizing sequence? So there could be a formation of bubbles of this kind. And I said it comes with a quantization. So if there is a formation of a bubble, you can prove that the energy that has to form is at least the Yamabe constant of the sphere. Therefore, if you can prove that the infimum is strictly less than the Yamabe constant of the sphere, then you don't have enough energy to develop a bubble like this. Okay, and therefore, minimizing sequences cannot form bubbling. Okay, so that's more or less the idea. How to prove okay, the weak inequality? That's rather easy. So I'll just give maybe I'll draw a picture. So prove that you have at least the weak inequality. Okay, so the idea is that on a small scale, every manifold, so I take my manifold, okay, so suppose that there is a hole, this is my manifold M. I can basically localize the infimum. So when I take the Sobolev quotient, the Yamabe quotient on the manifold, well, locally on a small scale, every manifold looks like a Ren. Okay, on small scales. Mg looks like Rn with a Euclidean metric. Okay, so you can use the Euclidean Yamabe quotient as a comparison on small scales on M. So basically you can take a function of the type u lambda, so very concentrated near a point P of the manifold, use a cutoff, and in this way you are able to approach the Euclidean Sobolev quotient as much as you want. So you take your function, which is very concentrated, very peaked, then apply a cutoff function, and then you get very close to this Euclidean quotient. So you can prove that Qg of u lambda times a cutoff converges to the Yamabe constant, to the Sobolev constant, Yamabe constant of Rn, which coincides with the one of the sphere. Okay, so therefore, it's rather easy to prove the weak inequality. But the previous proposition, so proposition 2, requires the strong inequality here. Okay, so let me comment now on the strict inequality. Okay, before I continue, is there any question? Okay, apparently not. Okay, so we already have some good, say, family of test functions for minimizers, which are exactly these ones. So we use the Euclidean extremal and glue it to a manifold, so we can approach certainly the spherical Yamabe constant. But can we go below that? So the hope is that the geometry of the manifold might help. And let me tell you how. Okay. So you can distinguish. So there is a tensor, so which is the curvature tensor, which distinguishes Rn from every other manifold. Okay, so there's a fact. So if I don't have time to introduce the whole Riemann tensor, but you can prove, so there's a theorem by Riemann that if the Riemann tensor of a metric G vanishes identically in, say, the neighborhood of a point P, so I take a neighbor U of a point P, so U is a subset of the manifold, then in U, in fact, the metric G coincides with the Euclidean metric. Okay, so the manifold must be locally isometric to Rn. But here we're dealing with the conformal geometry. So we want to distinguish a manifold conformally from Rn. Okay, so we want a condition which says when a manifold is conformal to the Euclidean metric. In fact, there is such a notion. Let me give a definition. So a manifold Mg is called locally conformally flat. So locally conformally flat if for any point P in M there exists U neighborhood of P and a conformal metric so conformal to G in U, which is flat. So such that the Riemann tensor of the conformal metric G tilde is equal to 0 in U. Okay? So we require that our metric G should be conformal to a flat metric. So one example is Sn, for example. So if you take Sn with a round metric, this is true because we saw by the stereographic projection that the round metric is conformal to the Euclidean metric. Another example is, for example, Sn minus 1 cross S1, so with a product metric. Okay, so this is another example, and there are many, many others. Okay, how can you tell such a thing? So Riemann curvature equal to 0 is a condition that tells you when the metric is locally Euclidean, okay? And for a metric to be locally conformally flat, there is another tensor, which is called the Weil tensor. It's the so-called conformal part of the curvature tensor. Okay. Probably I don't have time to say write it down, but there are more details on the notes, and you can certainly find many details either in textbooks or even on the internet. So it's denoted by WG, this Weil tensor, and it transforms nicely when you change conformally the metric, just as the conformal Laplacian does. So if you have a metric G tilde, which you can write as e to the 2 phi times G, okay, a conformal metric, then the Weil tensor with respect to G tilde is equal to e to the 2 phi, sorry, times WG. Okay, so this is not true for the curvature tensor. So if you take the Riemann tensor and you change conformally the metric, then the transformation law is very complicated. It involves derivatives of the conformal factor, while the Weil tensor transforms nicely in this way, so without any derivative of the conformal factor. It is not obvious because essentially the curvature involves second derivatives of the metric coefficients. So in general, if you change the metric conformally, you expect to see second derivatives of the conformal factor. But the Weil tensor has exactly these cancellation properties, so you don't see any derivatives of the conformal factor at all. So the transformation law is very simple. And there is this fact, so which I cannot prove now, but if the dimension is greater or equal to 4, a metric G is locally conformally flat. I write LCF if and only if the Weil tensor is identically equal to 0. Okay, and a remark is that if the dimension is 3, the Weil tensor is always identically equal to 0. Okay, there is another tensor, so the so-called Cotton tensor, does the same job. Okay, but I will not. I will only need the Weil tensor in what follows. So I just give it for your, say, general culture. Okay, so let me state one theorem. So this is due to Oban. Suppose that the dimension of the manifold is greater or equal to 6, and that the manifold MG is not locally conformally flat. So is not so this means that the Weil tensor is not identically equal to 0, okay, by the previous fact. Then we have the strict inequality. YMG is strictly less than YSN GSN. Okay, so as a corollary, is that under those conditions, the Yamabe equation is solvable. Okay, so it follows from proposition 2. Okay, so it means that when you consider a minimizing sequence, since the minimal energy is below the Yamabe energy, Yamabe constant of the sphere, then a minimizing sequence cannot form bubbling because the minimal energy is below the quantization threshold to develop bubbling. Okay, so bubbling cannot occur. So a sketch of the proof is in the notes that I can leave of that. Okay, let me just tell you briefly how this inequality is proved. So there is a useful result. So in the references that I gave, I quoted a paper by Lee and Parker. So there is this theorem. So this is due to Lee and Parker. So from it's a set of notes entitled the Yamabe problem from 87. They choose somehow nice conformal representative of the metric G. So they introduce what they call conformal normal coordinates. Okay, so probably you heard about the normal coordinates of a Riemannian metric. So when you choose a point P of a Riemannian manifold, which has a metric G, then there are optimal coordinates, which are called normal coordinates, which are defined using the geodesic flow from the point P. So conformal normal coordinates are chosen in two steps. So first, you choose a nice conformal deformation of the metric. Our problem is in fact conformal invariant. So if you choose, if you solve the Yamabe problem compared to, for one metric, and then if you change the metric conformally, then you find obviously another solution. Okay, so you can choose to start the conformal metric you want. And then once you choose that conformal metric, you can use normal coordinates for that other metric. So what they proved is the following. So you start from a compact manifold. Actually, it's not needed, but it's a local result. You take a point P in the manifold. Then, so the manifold is of dimension little n. For any capital N, so this is not a dimension, it's any integer number greater or equal than 2, you can find G tilde conformal to G near P, such that in G tilde normal coordinates, okay, so first you deform the metric conformally, and then you use the normal coordinates for the new conformal metric. So in these coordinates, you can make the determinant of the metric coefficients G tilde ij very close to 1. Okay, so R is the distance with respect to the metric G tilde from P. Okay, so you can make the volume element. So recall that the volume element, recall that the volume element with respect to the metric G tilde, this case, is the square root of the determinant of G tilde ij times the x. Okay, so the volume element becomes very close, as much as you want, to the Euclidean volume. Okay, so this is 1 plus big O of r to the n times dv Euclidean. Okay, moreover, it's not finished. So moreover, if you choose, so if this is technical, n is greater or equal to 5, then the scalar curvature Rg tilde is a big O of r squared. So you can make the scalar curvature at a given point equal to 0 and also flat, okay? And minus the Laplacian with respect to g tilde of Rg tilde is equal to 1/6 times the square norm of the Weil tensor of g tilde. At P. Okay, so the scalar curvature for the metric g tilde, if we fix the point P, and the scalar curvature behaves like this. It's a 0, it's flat, and it bends downward. Okay, so the Laplacian is negative. Okay, so how do we use this fact? Okay, application. So recall that QG of U is this quantity here. So it's the integral over m of Cn nabla U squared plus Rg U squared dV. And we can do everything with respect to G tilde. Okay, so I take QG tilde of U. And I need to divide by the integral of U to the 2 star dV G tilde to the power 2 over 2 star. Okay, so now so if we have coordinates x1, xn, are say G tilde normal coordinates at P, we can choose the test function U to be the Euclidean extremal in these coordinates, okay, for lambda large. So recall that in Rn, U lambda was a function like this, very, very concentrated. Okay, so what we're doing is the following. So we start from our manifold. So this is M. We choose the point P. Maybe the manifold has some topology. Okay, we choose now coordinates x. So these are g tilde normal coordinates. And we take in these coordinates x little u to be an extremal, a Euclidean extremal, very concentrated. Okay, then with a cutoff applied. All right, so let me also recall the Yamabe energy. Okay, so we can estimate each of these terms. All right, so it turns out that for this choice, so u of x, now it's really a radial function. Okay, we are using normal coordinates. So therefore, because, and also recall that the volume element dvg tilde is very close to the Euclidean one. So we can pretend, so the point is that we can pretend that dvg tilde is actually equal in the calculation so it's actually equal to the Euclidean volume. So therefore, we can estimate each of these three terms that appear in the Yamabe quotient. So this implies that the integral of Rm of the gradient of u squared is actually very close to the Euclidean gradient of u lambda squared, which is a given constant, and that the integral of u to the 2 star, so this is dvg tilde, so plus really lower order terms, negligible, and that the integral of the 2 star power of u is equal to the integral in Rn of u lambda to the 2 star. It's a positive function, but I take the absolute value, dvge, plus really lower order terms. And these lower order terms are really negligible. Okay, so what is left? So the thing which is more interesting is the scalar curvature. So recall also that the scalar curvature, Rg tilde, goes like this. And that the Laplacian with respect to G tilde of the scalar curvature at P is equal to minus 1/6 times the Weil tensor of G tilde squared. So it follows from a Taylor expansion so there are more details in the notes, that the integral of Rg tilde u squared dvg tilde. So this tends to 0 because this, so the sequence u lambda is converging weakly to 0. And by the Sobolev embedding into L2, so this is actually a compact embedding, so the integral of u lambda squared goes to 0. But you can quantify actually this thing here. So this is of order minus dimensional constant dn times the Weil tensor squared at P times lambda to the minus 4 plus lower order terms. There is an extra factor, say times log lambda, if n is equal to 6. Okay, so essentially, to understand this, so you can pretend that the scalar curvature is kind of radial here, radial and with a negative Hessian. Okay, so this integral has to do with so this is like lambda to the minus 4 times the norm of the Weil tensor squared at P times the integral of the norm of x squared times u squared in the x in Rn. So this integral is actually convergent if and only if the dimension n is strictly greater to 6. For n equal to 6, it's a borderline divergent, okay? And that's why you find an extra log in the Taylor expansion. Okay, so it's equal to this via a change of variables. All right, now, by assumption, so since the manifold, Aubin's theorem is assuming that the manifold, I'll show it again, the manifold is not locally conformally flat, so the Weil tensor is non-zero somewhere. Okay, so by assumption, there exists a point P such that the Weil tensor squared at P is non-zero. And therefore, you can prove that the Yamabe quotient, so Qg tilde of this u lambda, is equal asymptotically to the Yamabe constant of Sn minus some dimensional constant dn, norm of the Weil tensor squared, divided by lambda to the 4 plus times some log, if n equal to 6, plus lower order terms. So it is less than y Sn gsn for lambda large. Okay, so this proves the strict inequality and also the existence of a minimizer for the Yamabe energy. So a solution of the Yamabe equation. Is there any question? Okay. So let me discuss the remaining cases. So cases n less or equal than 5 or G locally conformally flat. So if the dimension is less than 6, the previous argument doesn't work. Or if the Weil tensor vanishes identically, also we cannot apply the previous reasoning. Okay. And so these were treated by Schoen in 84. And what he did was to use a more careful gluing of u lambda to m. Okay, so previously we just used cutoffs, and here it's not just cutoff. As we did before, okay? Oban essentially did that construction that I showed, and then used a cutoff. So the cutoffs are not so relevant in high dimensions, okay? Here the heuristics is the following, that if you look at the Yamabe equation, so say approximate Yamabe equation, so you can write the conformal Laplacian, say for say u lambda. So take lambda to be very large, and take a Euclidean extremal which is glued to the manifold. So Lg of u lambda is close in some sense to u lambda to the n plus 2 over n minus 2. So distributionally, so this behaves distributionally. So you can check it via a change of variables, like 1 over lambda times the Dirac mass at the point P. Okay, not like a Dirac delta, but a Dirac delta times a small multiple. Okay, so it is natural to consider the Green's function say, let me call it GP of LG of the conformal Laplacian with pole at P. Okay, so the solution LG of GP equal to the Dirac delta at P. So the Green's function, you can show it exists because lambda 1 of LG, we're assuming it to be positive, okay? And therefore, the operator LG is invertible. So there are abstract theorems telling you that when you have an invertible elliptic operator, then you can find the solutions via a representation formula. So a Green's function exists. Okay, so you can expect because of this sort of distributional equation, the thing is, it is natural to consider, so consider, say, test functions say phi lambda such that say phi lambda is sort of close to u lambda near P, and it's close to 1 over lambda times the Green's function away from P. Okay, because of this property, say the distributional conformal Laplacian of u lambda. So since it looks very close to a Dirac delta, then it is natural to consider a test function which basically satisfies this distributional equation everywhere on the manifold. So if you do this, if you interpolate between the two, then the effect, you don't have such a strong effect that you would have from the cutoffs. Okay, so basically more precise than just cutoff. Okay, and there is this proposition so the Green's function has an effect in the expansion of the Yamabe energy. So if n is less or equal to 5, or if G is locally conformally flat, so which are the cases I'm considering in the slides. Okay, so if the dimension is low, or if the metric is locally conformally flat, then in normal or G tilde in conformal, normal coordinates at P, one has that the Green's function, Gp, writes as the Euclidean Green's function plus some constant A, some bounded term, plus a big O of R. Okay, so you have an expansion of the Green's function which is very similar to the expansion of the Green's function in a domain. And there is a deep theorem by Schoen and Yau so from 79, 81, and 84, so it's in different papers. Okay. They tell you that if under the above assumptions, so in dimension less or equal to 5, or if the manifold is locally conformally flat, so if the manifold is not the sphere, or not conformal to the sphere, then this constant A is actually positive. So actually they have a formulation in general relativity. So this is called the positive mass theorem. But a consequence of that is that you understand the lower order term in the expansion of the Green's function. So it's a quantity that tells you, that distinguishes the sphere from any other manifold somehow. Okay, and once you have this, so the positive mass theorem, so let me recall both theorems and the definition of the test function that I chose, this one. Okay, so I just copy on the next slide. Okay, so then Schoen proved so he proved that when you evaluate the Yamabe quotient on the function phi lambda defined above, so here with this careful gluing, then this is equal to the Yamabe constant of Sn minus a divided by lambda to the n minus 2 plus lower order terms. Okay, so this implies again the strict inequality. So y mg. So you produce test functions for which the Yamabe energy is strictly smaller than the spherical one. And the Yamabe problem is solvable. Okay, so a couple of comments. So Schoen asked for this question. So problem so this was posed by Schoen in the 80s. So are positive solutions of the Yamabe equation uniformly bounded? And I believe this is treated in Yanyan's course. So the answer is surprising. They are if the dimension is less or equal than 24. Otherwise, there are counterexamples, dimension 25 and higher. A couple of remarks. Is that in dimension 2, equations, so when you look at the conformal change of the Gaussian curvature, this type, so equations are of exponential type. And even say within the organizers of the event, so there are experts in this kind of equation. And the other remark is that I stated the uniqueness of solutions when the first eigenvalue, when the curvature is negative, so when lambda 1 of Lg is negative. The other remark is that instead, if R bar is positive, solutions of the Yamabe equation may not be unique. So there's an example by Schoen already on S1 across Sn minus 1. And there is more recent work, for example, by Bettiol, Piccione, and Sire. So Yannick is involved in this event, both as a speaker and as an organizer. And they use bifurcation theory. So to show that there can be actually many solutions and they can produce examples in which the number of solutions is actually going to infinity. Okay, so I stop here. Is there any question?
Hi, sir. Sir, in the application part, in Taylor expansion, you are wrote integration will convergent for dimension n is greater than is equal to 6. So,
Exactly, yes.
but what about lower dimension? I want to
Okay,
know what is the problem with lower dimension?
yeah, in lower dimension, in fact, this approach doesn't work. And you need to use this approach by Ricci. So you need to be more precise. I can explain, say, qualitatively why there is a discrepancy in the method within low dimension and high dimension. So notice that the profile you use, so we use the profile u lambda of x, which is lambda to the n minus 2 over 2 u of lambda x. And u of x is 1 over 1 plus x squared to the power n minus 2 over 2. And this at infinity behaves like x 1 over x to n minus 2 at infinity. Okay, so you notice that if n is large, decay is faster. Okay, so the consequence is that the contribution from the geometry is local if the dimension n is greater or equal to 6. But it is global, so global if the dimension n is greater or equal than 5. Okay, so this number a that we saw, which enters in the expansion of the Yamabe energy, so this constant a is not a local quantity, it's a global object. Okay, and that's why this case is more difficult. So you cannot use those integrals, they are divergent. And what enters in the expansion is some global quantity, so which is more difficult to understand. And that's why this theorem by Shen and Yao is very deep.
Can you hear me? Yeah.
Yes?
Yeah, in positive mass theorem, this A is positive for any dimension n, or only for n less than equal to 5?
Here, okay, here I'm assuming n less or equal to 5, or the manifold locally conformally flat. In fact, for this result, they proved it for n less or equal than 7, or the metric G locally conformally flat. Okay, because for this proof they use the minimal surfaces. So use the minimal surfaces. So basically, the argument goes by contradiction. If the mass is negative, you can construct some stable minimal surface, but then you can use the second variation of the area and the positivity of the scalar curvature to show that these surfaces, these minimal surfaces, are unstable. And more recently, in 2024, they have a proof for general n. But for the Yamabe case, you only need it when the dimension is less or equal to 5, or the metric is locally conformally flat. So for this application, the result of the 8 was enough.
Thank you.